So welcome to Trig, and we are going to begin by looking at some functions that hopefully should be vaguely familiar to you from GCSE, and that is the functions of sine, cos and tan. So we're going to begin with a unit circle. It's a unit circle because it has a radius of length 1, and you can see here that I've drawn a little triangle in basically around the axes. And we're going to explore what happens to the various sides of this triangle as I change my base angle x. So the first thing we're going to have a look at is the height of this triangle. Now, if you think back to GCSE Trig, soccer toa as we tend to call it, then in this little triangle here with our base angle x and our hypotenuse of 1, this is our opposite side. Now we know that the opposite and the hypotenuse are in a relationship with sine. So sine of the angle is opposite over hypotenuse. In this case, we've got sine x equaling the opposite divided by a hypotenuse of 1, don't forget that unit circle, and hence the opposite side can be described as sine of x. So by exploring what happens to the height of the triangle, I'm hopefully going to be able to generate the curve for sine of x. So let's start with a super small angle, i.e. basically so small that the triangle is almost flat to the horizontal axis, in which case our height is going to be exceptionally small. And indeed, if we have no angle to this triangle here, we're just going to end up with a flat line along the x-axis, and hence our function for sine starts at the origin. So our x-axis here is our angle, and y is the height of the triangle, which represents sine x. As we start to increase the value of x up to the right angle, so up to 90 degrees or pi by 2 radians, my height of my triangle starts to increase. So here's a slightly bigger triangle, bigger value of x, an even bigger one. Again, the height in each case is increasing. So we're going to find that as we go round from that horizontal line up to the 90-degree point, the height of the triangle we're creating is increasing. Trend those red lines that I've drawn there. And in fact, it becomes so tall that it then occupies the entire radius of the line vertically at pi by 2. So we have a height of 1 at pi by 2. As we extend our angle even further from that positive horizontal axis, we're coming around to triangles like this. And actually we end up drawing them on the other side, just basically so it's a bit clearer. You can see that as we extend that angle around, we're actually finding that the triangle height is reducing again. And it's going to keep reducing down until we hit the horizontal axis at a semicircle, so 180 degrees or pi radians. So we end up back at 0 at 180 degrees or pi radians. We carry on around, so now we're dipping below the x-axis. And again, if we draw in our little triangle, it would look something like this. And as we start increasing our angle around, the height of that triangle starts to increase again, but it was once going up and now it's going down. And we need to show that change of direction. Thinking about potentially your mechanics topics, if you studied them, we like to show changes of direction by showing a change of sign. So we could call these ones negative, and that makes sense, right? We're below the x-axis now. So if this is our y-axis, we're below the x-axis, we're in negative y values. So we are increasing in the negative direction, going and going and going until we hit 3/4 of the way around the circle, or 270 degrees. So that's 3 pi by 2, or 270 degrees, at which point we have sat back on the y-axis again. We're at -1, the full length of that radius. And then as we come into the final quadrant, so this time we're going all the way around to these sorts of areas, our triangle, as we continue rotating round, is getting smaller and smaller and smaller, and this is the height of the triangle, don't forget, back up to our horizontal axis, our positive horizontal axis, at a full rotation, so 2 pi radians or 360 degrees. And hence the shape of our sine curve for a full rotation of a circle is a very nice, although slightly not so nice at the bottom there, I managed to make that a bit sharp, oscillating curve. So gently rises, gets its maximum at pi by 2 radians, comes back and intersects the x-axis at pi radians or 180 degrees, minimum at 3 pi by 2 radians or 270 degrees, and returns back to where it was at 2 pi radians. If you carried on going around, you'd start tracing the place that you had already been, but that's a legitimate thing to do, in which case the pattern continues as we continue to increase our x value, i.e. we rotate round the circle maybe another time or multiple times. And if we want to think about the negative direction, well, that's a bit like we were going that way around the circle in the positive direction. Negative is going around in the opposite direction. So it actually continues our pattern, but kind of going negative first. But that allows that oscillating pattern to keep repeating as time goes on. If we think this time instead about the base of our same triangle, so the same unit circle, same base value of x, but this time think about the base of the triangle, we would again go back to our trig relationship, so SOHCAHTOA, and figure out that that is actually cos of x. So by looking at how the base changes, I should be able to create the curve for cos. Now, thinking back again to where our angle is 0, we would have no triangle effectively, or in fact a triangle of no height, in which case the base of that triangle is the full length of the radius at that point. So when x is 0, cos of x is the full length it could possibly be, i.e. it's 1. So again, our x-axis is representing our angle, and this time our y-axis is representing cos of x. So this time we're starting with the full base length being 1, and as we go around this circle, so start to increase the value of x, our triangle is getting taller and skinnier. So the base at each point is coming in, it's reducing until we get to that right angle where we have no base and full height. So our cos graph is going to go through the x-axis at pi by 2 at that right angle, 90 degrees. At that point we have a straight line vertically up, so we have no base. Moving around then to 180 degrees or pi radians, as we start moving along those triangles, so again we've kind of tipped over that point and we're coming around at this point. If we have a look at the base this time, it starts off relatively skinny and then widens even more and widens even more, but going in the opposite direction. So again, we flipped over the y-axis. We were out in the positive x direction, we flipped over the y-axis, and now we're increasing in the negative x direction out to the full extension of the circle, so 1, but in the negative direction, so minus 1 at 180 degrees or pi radians. As the triangle tips over, because our angle has increased past 180 degrees, our base of our triangle is shrinking again back down to 0 at 270 or 3 pi by 2. And then we're going to come full circle, so our base of our triangle increasing back around again as we go around, back out to that full extension of the radius, so back up to 1 at 2 pi or 360 degrees. And hence our cos graph is that same oscillating shape, which has been shifted around a little bit. Oh, apologies, I've just pulled that in terribly. And again, you could go around the circle and your pattern would continue. You could go the opposite way around the circle, and again, your pattern would continue in the opposite direction. So we get this continuous wave pattern for both sine and cos. Now, tan is a little bit different. So let's go back to our trig relationships from GCSE, so SOHCAHTOA, and we know that tan is the opposite divided by the adjacent. Now, from our previous two graphs, we know that the opposite, for as long as our angle is, of course, the base one, that's the non-right angle one, our opposite is sine and our adjacent is cos. And that actually gives us a relationship that we'll come back to in another video, but that tan x equals the opposite, which is sine x, divided by the adjacent, which is cos x. So to think about how tan x is going to look, we could start to think about what the relationship looks like between those two graphs instead. So let's think about what happens when x is 0. So we've this time got x on the x-axis, the angle of rotation, and this time y is representing tan x. So when x is 0, sine is 0, and cos is 1. So tan of 0 is x is 0 and cos is 1. Well, that's fine. That's just 0. Scooch around to pi by 2 or 90 degrees, and tan of pi by 2 is, well, sine is 1 at that point, but cos is 0. And if you try and divide one thing into nothing, you have to essentially explode it into an infinitely large number of absolutely minuscule pieces, i.e. it's undefined there. So we actually have an undefined point at pi by 2 or 90 degrees, and we demonstrate this actually with an asymptote line because of the behaviour of tan around that. So we'll come back to that in a minute. Again, we could look at tan of pi or 180 degrees, and we get this pattern again, except we end up with a minus here. So for 180 degrees, sine is 0, cos is -1. So we get another 0 at pi or 180 degrees. We get a similar issue for tan of 3 pi by 2 or 270 degrees, again with a minus, but the point is we're dividing by that 0. We're going to pop in an asymptote line because of the behaviour of tan around those points, and then we come back around to 0 at 2 pi or 360 degrees, again because we actually end up back at that equivalent point for 0. Now, if we think about the behaviour between 0 and 90 degrees, or 0 and 2 pi radians, we start off with sine being something really small and cos being as big as it can be. When we get very, very close to 90, cos is basically so small it's almost 0. So it's like, you know, think about 0.1, then 0.01, and then 0.001, and then 0.0001. And of course, if you're dividing a fraction by a very small number, so we're approaching 1 divided by almost 0, the fact that that's a super small number there on the bottom means that the fraction overall is going to be massive. So tan ends up shooting off to positive infinity. Now, of course, it can't reach it, but we're getting infinitely close to 90 with an infinitely large number, and hence the asymptote line there. Between 90 and 180, we've got a negative to play around with, but we're kind of doing the reverse thing. We actually end up with something infinitely small coming up to 0, and then we're basically repeating the pattern again. So our tan graph looks like that. So we go from 0 to something infinitely large because you have something really, really tiny on the bottom of the fraction. You're then working backwards from that with a negative, back up to that situation where there's a 0 on the top of the fraction, and then you're going spiralling off again with the same pattern. So our three functions laid next to each other, so you can see how they line up with each other, and these guys are between 0 and 2 pi, or sorry, minus 2 pi and 2 pi, or minus 360 and 360, each one of them. You can see that you have got those kind of key points where everything is lining up. So sine and tan are both 0 at the origin, cos is 1 there. Where cos crosses the x-axis, I's got those zeros. There are those asymptote lines for tan. And we can see how often these patterns repeat. So sine and cos repeat every 2 pi radians or 360 degrees. Every time you count through 360 degrees, you've got the same pattern again. That's true for both of those two. They are the same graph, just translated. Whereas tan, you actually have the same pattern repeating every pi or 180 degrees. So if you go from 0 to pi, that's the same pattern as from pi to 2 pi. This is called the period of the function, and it is something you need to know about these 3 functions for your A-level exams. So you do need to know that the period of sine and cos are 2 pi or 360. So here's our sine graph and our cos graph. And you need to know that the period of tan is 180 or pi radians. So the only other thing to mention very briefly, which sets us up for the next video, is where there are lines of symmetry in these graphs. Tan has no lines of symmetry, not vertical or horizontal ones anyway, in fact none, but you do have lines of symmetry in sine and cos. So sine is symmetrical around its maximums and minimums, so is cos, but where they are obviously differs. So if I were to put a mirror down the line x equals pi by 2 or x equals 90, same place, you'd see the same pattern emerging on both sides of that mirror line. So there's a line of symmetry. Same for 3 pi by 2, same for minus pi by 2, same for minus 3 pi by 2. So those are those lines of symmetry on sine. For cos, that would be 0, pi, and 2 pi. And this can be really helpful when it comes to thinking about where the same points on the graph appear, i.e. solving trig equations, which we're going to do in the next video.